Hi, AP Stats. This is Mrs. Harding. This is lesson 9.1b. On the screen, you'll see the learning targets for chapter 9. In 9.1a, you address the first learning target there, state the appropriate hypotheses for a significance test. Today, what we're going to cover is to interpret a p-value in context. So we'll define what a p-value is, and then use that p-value to make an appropriate conclusion for a significance test. So go ahead and turn to lesson 9.1b in your OneNote notebook. If you recall from 9.1a, there was the problem about the player who claimed to make 80% of their free throws. And we stated that the null hypothesis then is that P is equal to 0.8, where P is the proportion of free throws the player makes. That is their claim. Then, based on a sample in which the player only made 58%, we came up with a probability that that would happen. We estimated the probability that a player would make 58% or less, given the null hypothesis was true, was only 1 out of 500. We've talked about this concept before, but this has a name. That is called the p-value. So that probability, 1 out of 500, is called a p-value. The definition there is right below. The p-value is the probability, assuming the null hypothesis is true, that the statistic would take a value as extreme or more extreme than the one actually observed. This is called the p-value. And note that the smaller the p-value is, the stronger the evidence against the null hypothesis. The p-value is the probability of getting a sample as extreme as what we might have. The smaller that probability is, the less likely that this has happened just by chance. So then there is stronger evidence against the null hypothesis. And down here at the bottom, one good way to think about this is as a conditional probability. And you can see the statement down here at the bottom. P, the p-value, is the probability that p hat, the sample statistic, is less than or equal to 0.58, given that the population parameter is 0.8. So if this is true, what's the probability of getting a sample as the one that we got? And that answer was only 1 out of 500. That is the p-value. Head to the second page here. We're not going to calculate any p-values today. We're just going to talk about interpreting them in the context of a problem. Recall the job satisfaction problem that was discussed in 9.1a. You have the null and alternate hypotheses there. Mu of the difference is equal to 0 is the null hypothesis. And then the alternate hypothesis is that the mean of this difference is not equal to 0. And the difference meaning the self-paced rating minus the machine-paced rating. The first question there is explain what it means if the null hypothesis is true in this setting. Well, if the mean of the difference is 0, then that would mean that there is no difference in their ratings. The average rating for the machine and the average rating for the self-paced is no different. And then the alternate is saying that there is a difference. So then in here it says, suppose data from 18 workers gave X bar to be 17 and standard deviation to be 6. That is, in the sample of workers, they rated the self-paced environment on average 17 points higher. So then when we go through and try to determine what this means, in part B, researchers performed a significance test using the sample data and obtained a p-value of 0.2302. And again, you can see here the conditional distribution piece, the probability that X bar is greater than or equal to 17 or X bar is less than or equal to negative 17, given that the mean is actually 0. What is the probability of that happening? And they came up with 0.2302. So you can see in here, interpret this p-value in context. If there is no difference in the average job satisfaction ratings the company uses for self-paced or machine-paced, then the probability of us getting a sample where the average difference is 17 or more is about 23%. Not a huge percentage, but certainly not one that would call into question the null hypothesis. All right, on the next page, do the data provide convincing evidence against the null hypothesis? And explain. That was kind of what I just said. A 23% chance of happening is not too unlikely to cause me to suspect that the null hypothesis is false. So a 23% chance of something happening isn't so small that we'd go, oh, that's suspicious if it does happen. So in part D, in the previous question, you probably concluded that there was not enough evidence. Does this imply that the null hypothesis is definitely true? This is an important concept and it's often a missed idea. We are never actually proving whether the null hypothesis is true or not. So just because you fail to disprove it doesn't mean that you're saying it is true. So you want to avoid using that kind of wording. And in the answer that's on the screen there, no, our sample results may be misleading us to an incorrect conclusion, which is always a possibility. We're making a judgment call based on the evidence that we have in front of us, and it is possible that we make a misjudgment one way or the other just based on our sample. Part E, suppose now the researchers performed a significance test using the sample data, and they obtained a p-value of 0.018 instead. Interpret this value in context. All right, thinking back to the conditional probability, we know that if there is no difference in the job satisfaction ratings between self-paced and machine-paced, then the probability of getting a sample that these researchers had used with an average difference of 17 or more is 0.018. So you can phrase it just in the form of a conditional probability. If the null hypothesis is true, the probability of getting a sample like what we're looking at is 0.018. So now is this evidence against the null hypothesis? Yes, in this case, 1.8% chance of something happening is pretty unlikely. So we have reason to believe that the null hypothesis is true. We're not going to say definitively the null hypothesis is false. We just have evidence to believe, evidence to lead us to think that the null hypothesis is true. And we're going to reject the null hypothesis. So then in part G, does this imply that the null hypothesis is definitely false and that the alternate is in fact true? Again, we can't say that. Even though 1.8% is very small, all we can say is that we have strong evidence against it, but there is that tiny, tiny percent chance that the sample we got is fine. We just got unlucky with that small sample, and it may be misleading us to an incorrect conclusion. So as always, we're just talking about the strength of evidence against the null hypothesis. Either we have strong evidence against it or we don't have strong evidence against it. Moving on to the next page. Here it summarizes what I've been saying underneath the important comment. When conducting a test of significance, we never say the null hypothesis is true or the null hypothesis is false, since there's always a chance we would be incorrect. So instead, we say that we have evidence to reject. So that means there is strong evidence against the null hypothesis, so we're going to reject it. Or we fail to reject. We do not have enough evidence to reject it. In statistics, we never prove or disprove definitively the null hypothesis. We only provide evidence against it or not and comment on the strength of the evidence. So then how strong does the evidence have to be? Well, up to this point, we've talked about the 5% cutoff, that we've said that anything that has less than 5% chance of happening is considered a rare event. So this leads us to the idea of something called statistical significance. So because we would come up with something that had such a small chance of happening, it's a rare event, we would call it statistically significant. And if you scroll down on here, I'll give you, oops, my screen's not moving. There we go. So remember, the smaller the p-value, the stronger the evidence against the null hypothesis. The larger the p-value, the weaker the evidence is against the null hypothesis. But this cutoff level for what is statistically significant is called the significance level. Like I said, we've been using 5%, but it's actually somewhat subjective depending on the scenario. Some people use 5% as the cutoff. Some people use 1% as the cutoff. Sometimes you could use something as high as 10% or as low as 0.1%. But whatever this is called the significance level, or it's called the alpha level. And you should decide on that in advance of starting your significance test. So then if your p-value is below the alpha level, you have statistically significant results and you can reject the null hypothesis. If your p-value is larger than the alpha level, you do not have evidence and you fail to reject the null hypothesis. We will still typically stick with 5%, but just be aware that this is a changing thing. Some researchers use different levels, and it sort of depends on the situation. On the next page, there is an example problem. Check your understanding. I will leave that up to you to try on your own, and then check with the answers in your OneNote. If you have any questions about it, be sure to bring that up during class. Let's head to the following page. And it says at the top there, don't confuse statistically significant with practical significance. Statistically significant does not necessarily mean important. It simply means that it's not likely to happen by chance. Let's take a look at this example number 4, comparing a new antidepressant against an older antidepressant. It says you conduct a completely randomized double-blind experiment where you compare patients taking the new drug to patients taking the old drug. The questionnaire they fill out gives you a possible score of 100, where 0 to 24 puts the patient at high risk, 25 to 50 is moderate, 50 to 75 is low, and 75 to 100 is normal. So in part A, they conduct a test in which the p-value for the test is 0.014 and the alpha level is 0.03. What should you conclude? All right, looking at those numbers right now, we notice that the p-value is less than alpha. So therefore, we can reject the null hypothesis that there is no difference between the drugs, and we have evidence to say that there is a difference between the drugs. The results are considered statistically significant. Part B, the results of the test show that the average depression score for the patients taking the older drug was 30.6, and for those taking the new, more expensive drug, the average was 31.42. Is there a practical difference in the results? And this is the point of this. That difference between 30.6 and 31.42 is really small. Both are still at, was that moderate risk? Yeah, both of those are still at moderate risk for depression. So even though it's an improvement that is statistically significant, it actually doesn't really tell you much about the drug working better. In that last example, you notice that we used an alpha level or significance level of 3% as opposed to 5%. So if you take a look here, what's the point of even choosing a significance level if it can vary? Well, that depends on two different things. How high or low we make this alpha level. The first one there says, how plausible is the null hypothesis? If the null hypothesis represents an assumption that the people you must convince have believed for a very long time, it's going to take stronger evidence to prove or to change their minds. And we would need something smaller than, we would need a very small p-value to convince people. So if it's a very, very long held belief and we run some research that has a p-value of 8%, it's probably not strong enough to convince people, as opposed to if we put our cutoff level, our alpha level at say 1% or 0.01%. And then the second criteria there is kind of a big one. What are the consequences of rejecting the null hypothesis? You notice that a lot of our examples have to do with medicine, health, drugs. If rejecting the null hypothesis in favor of the alternate hypothesis means making an expensive change of some kind, you need strong evidence that the change will be beneficial. So if you think about that last example where they said the new depression drug was much more expensive, you're going to need pretty strong evidence to convince people that they should be buying this more expensive drug. These criteria are a bit subjective. Different people will insist on different levels of significance. Giving the p-value allows each of us to decide individually if the evidence is sufficiently strong. And you can see typical levels would be 10%, 5%, 1%. Any researcher can decide which level is appropriate for their. So this brings us to the end of lesson 9.1b. I skimmed a couple of pages. So again, if you have questions, make sure that you ask in class, and you have a very nice day.